So for Unit 8 review, we're talking about acids, bases, buffers, and titrations. You can read through those. Here are the equations that we're going to be seeing throughout the unit. So Kw is the equilibrium constant for water. It's going to be dependent on temperature. Because it depends on temperature, if it's asked, is this solution acidic, basic, or neutral? The thing that's always true is H has to equal OH, as opposed to pH is equal to 7. Because as the temperature changes, then the pH of neutrality is going to change. Also, if you have more hydrogen ions, the solution is going to be more acidic. If you have less hydrogen ions, then that means you have a higher pH. Here we want to calculate the pH of a 0.1 molar solution of potassium hydroxide. The first thing you should realize is that it is a strong base because it's a group 1A hydroxide. Next, when that breaks apart, it produces 0.1 of potassium and 0.1 of hydroxide. So what we care about is the hydroxide. So POH is equal to the negative log of OH. So negative log of 1 times 10 to the negative 1 is simply 1. pH plus POH is equal to 14. So 14 minus 1 is equal to my pH, or 13. Anytime you negative log without a calculator, if it's 1 times 10 to the whatever it is, then it's going to be the exponent in positive. So 1 times 10 to the negative 9th would be 9 when you negative log that. So we will need to be able to calculate pH and POH of strong acids and bases. Your strong acids are those 6 listed there. They completely ionize in water or aqueous solutions to produce hydronium ions. As such, the concentration of hydronium is equal to your concentration of H. Same thing with our strong bases. Our strong bases are going to be group 1A, 2A hydroxides. They also completely dissociate to produce hydroxide. So go ahead and pause the video and calculate your pH of these two acids and bases. Restart when you have your pHs. Well, since that's a strong H, or strong acid, my concentration of H is 0.3 molarity. So my pH is 0.52. The second one was a little tricky because I have 2 hydroxides. So when that breaks apart, I produce 2 hydroxides for every 1 calcium hydroxide. So POH is equal to negative log of 4, not 2, which is negative 0.6. So 14 minus negative 0.6 is equal to 14.6 for the pH. So your pH generally goes from negative 1 to 15. If we were to draw a representation of these, let's go ahead and draw 3 molecules of HBr and 3 molecules of calcium hydroxide. Well, because they are strong, they should break up 100%. So that would be my bromium, or HBr, and then calcium hydroxide. I get 3 calcium, but I should get 6 hydroxides. You also need to be able to calculate the pH of weak acids and bases by setting up a Rice chart and then plugging them into your equilibrium expressions. You can go ahead and pause and read through the rest of these. Majority is talking about weak acids and weak bases only breaking up a small amount. So the majority is going to remain unionized. You also need to be able to calculate the percent ionization. Percent ionization is X over initial times 100. So my weak acids and bases do not dissociate 100% completely. Therefore, we need ice tables. We know this is a weak acid because it's not one of the 6 that we just saw that we need to have memorized. And they gave you a Ka value. If they give you a Ka, it must be a weak acid. So step 1 is I'm going to write my dissociation equation. And set up my ice chart. I have initially 0.4, 0, I'm going to go ahead and write my equilibrium expression. So always good habit to write your expression before plugging it in. And they gave me the Ka, so now I just need to plug everything in. From Unit 7, we saw that when equilibrium constants are very large, then they basically go to completion, and we can do stoic. In this case, my K value is so small that I can ignore this minus X, because 0.4 minus a really small number is basically still going to give me 0.4. So we're going to have so few products that we can say that when it's a subtraction or addition of those amounts, that they're not going to affect the difference more than 5%. So here we're going to multiply by 0.4 and then square root to get my X. Make sure you always define what X is. That's important for calculating my pH. In this case, my H is my X. So solving that out, I get 0.00268. So pH is negative log of H. So my pH is 2.57. If I was to draw 3 of these acetic acids in the beaker, the majority of them should be still together. I may break apart 1, only since there should be some hydrogen ions in solution since I do have a pH. But really about 1 in 10 of a weak acid will break apart. So you could also say that when drawing it, all of them should be together because I'm only representing 3 of the molecules versus at least 10 of them. But at most you could have broken apart is 1. So go ahead and pause the video and calculate the pH of this one. Notice they gave you a Kb, so this should be a base. And for our bases, remember that they have to react with water because it's got to gain a hydrogen from somewhere. So that should have been the equation that you wrote. Although we have to write water in our equation, we don't want it in our ice table so we don't accidentally mess it up when we plug it into our Kb expression. So then your Kb expression is still products over reactants. Just as before, we can ignore that minus X. So multiplying and then square rooting, my X in this case is going to be my OH concentration. So I've got to find my POH by negative logging that value. And then my pH is 14 minus that. Since it's a base, I should have a pH greater than 7, which I do. And just as before, if I was to draw a representation of this, the majority of it is still going to be together. And I may have one that is now broken apart due to gaining a proton from hydrogen. We can also calculate the percent ionization for that last problem. Remember, percent ionization was our X value, aka how much of it broke apart, over the initial value, or initial concentration, times 100. Well, our X we solved for on the previous problem. It was our concentration of OH. If it was an acid, it would be our concentration of H. And then our initial concentration is right there. Multiplying by 100, we get 2.34%. Notice that's less than 5%. Had my percent ionization been over 5, then I wouldn't have been able to ignore that minus X. So go ahead and draw a representation showing 10 molecules of each of these compounds, HCl and HNO2. Restart when you're done. So my HCl should have broken apart completely, so there should be 10 H's, and I should have 10 chlorines. While HNO2 is a weak acid, so my weak acid should have one of them broken apart, and then the rest of them should still be together, so that's 2. So again, our difference between a strong acid and a weak acid is our strong acid breaks apart 100%, giving us lots of H's, while our weak acid breaks up only a small amount, producing a much smaller percentage of hydrogen ions, even though they're the same molarity. So if we know the percent ionization or the pH of an acid or base, we can calculate the Ka of it. So go ahead and pause and try to figure this one out on your own. Restart when you're done. We don't know what the weak acid is, so we can just use the general formula. HA breaks up into H and A. We can set up a rice table. To find my Ka value, I need to know my concentration of H, concentration of A, and my concentration of HA. So given the percent or the pH, I can find X, because remember, percent was X over initial times 100. So I don't know my X, but my initial is 0.025, and I know my percent is 8.30. So dividing by 100, multiplying by 0.025, I get X is that value. So I can plug that X into my equilibrium line of my ice chart, and I get X squared over 0.025 minus 0.002075. Although that may not matter much on the bottom, always subtract it out if you know what X is. I have a calculator, so I can easily plug that in, and I get 1.88 times 10 to the negative 4th. Salts can also be acidic, basic, or neutral. A salt is neutral if it comes from a strong base and a strong acid. So if I was to break this apart, put OH on the first one and an H in front of the second one, I could say this came from NaOH and HBr. The stronger an acid, the weaker its conjugate. So NaOH is a strong base, so its conjugate Na must be neutral. HBr is a strong acid, so its conjugate Br must be neutral as well. So neutral and neutral makes neutral. A salt is basic if it came from a strong base and a weak acid, so same thing. NaOH is a strong base, so Na is neutral, while acetic acid is not one of the strong acids, a weak acid, so its conjugate should be basic. So this salt is basic. And the last one, doesn't come from ammonium hydroxide. It actually comes from ammonia, NH3. But we can say that that's a weak base, and that means its conjugate, NH4, must be a weak acid. Cl came from HCl, which is a strong acid. Since it's strong, its conjugate will be neutral. So acidic and neutral means that this is an acidic salt. So on this one, we're also trying to find our Ka, but this time they gave you the pH. So this should be similar to that one that we saw a minute ago. So go ahead and pause and see if you can solve this one without a calculator since it's multiple choice. Since they gave you the pH, 10 to the negative pH is equal to concentration of H. I get that from rearranging the pH equation. So 10 to the negative 3 is equal to my H concentration. Plugging it into my Ka expression, I get 1 times 10 to the negative third squared over 1 times 10 to the negative 1 minus 1 times 10 to the negative third. Simplifying that down, I get 1 times 10 to the negative 6th on top because I multiply my exponent by my negative 3. And on the bottom, even though we said a second ago, don't ignore your minus x, because we don't have a calculator, our answer choices are far enough away that we can just say this is 1 times 10 to the negative 1 on bottom. Therefore, my answer is 1 times 10 to the negative 5, because negative 6 minus negative 1 gives me negative 5. So my answer is B. Go ahead and pause the video and read through the different types of acid-base mixtures that you may see on the test. Restart when you are done. So before starting this one, let's go ahead and figure out what the substances are. Are they strong acids, strong bases, weak bases? So like for this first one, that's a strong acid and this is a strong acid. Go ahead and do that for the next 4. Restart when you're done. You should have said this was a weak base. We know it's a weak base because in this next problem, they give you the Kb of NH3. And KOH is a strong base. So this one's a weak base. And NH4Cl has 1 extra hydrogen, so that's a weak acid. These two are conjugates of each other. So now we can look at it. The first two are both strong acids. You may not see a problem where they're both strong acids, but if you did, all you have to do is say that the concentration of H is 0.3 plus 0.2 or 0.5 because they're both strong. They're both going to break apart 100%. So my pH is equal to the negative log of 0.5 or 0.30. For B, I have a weak base and a strong base. Well, a strong base breaks apart 100%. My weak base is only going to break up a small amount in comparison to my strong base. So kind of like I can ignore a plus or minus x, I can say that my concentration of OH is just 0.4, and I can ignore that weak base. So my POH is negative log of 0.4. So my pH is 14 minus my POH, or 13.60. And this last one is a buffer. We have a weak base and its conjugate. So when we have a buffer, we can use pH equals pKa plus log of the concentration of my base over my concentration of my acid. pKa is simply negative log of my Ka. They didn't give me a Ka though, they gave me a Kb. So we have to use the equation Kw is equal to Ka times Kb. Kw is 1 times 10 to the negative 14. That over my Kb is going to give my Ka. So for my pKa, I negative log my Ka plus log of my concentration of my base. Well, this is my weak base, so 0.2 over 0.3. and my pH is 9.08. If I had equal concentrations of my weak base and weak acid, my pH would simply equal my pKa. We'll be talking more about that later, but since I had more acid than base, my pH is less than pKa. You can go ahead and read through this page, paying close attention to the underlined pieces. So, titration curves. This one, we're starting at a pH greater than 7, so we're starting with a base. The only way you can figure out if this is a strong base or a weak base is to look at the equivalence point. The equivalence point is the midway section of this somewhat vertical line. Since our pH is less than 7, this must be a weak base. So at the very beginning of the titration, we only have a weak base present, so we would calculate the pH based on that weak base. Well, this is the equivalence point. And the equivalence point is when moles of acid equal moles of base. For a weak base by strong acid titration, only the conjugate acid remains at the equivalence point, and that's why our pH is less than 7 for a weak base by strong acid titration. It took 50 milliliters to reach the equivalence point, so halfway to equivalence is 25. So this is halfway to equivalence. And if it's the halfway to equivalence point, then pH will equal my pKa. And notice that the graph isn't changing very much in pH around the halfway to equivalence point because that's where max buffering occurs. We have roughly the same amount of conjugate acid and weak base. That's when pH equals pKa, is when my concentration of my weak base equal its conjugate acid. And so around that section we have max buffering, meaning the pH isn't going to change much. Then after the equivalence point, only excess strong acid affects pH. So the two most important parts of a titration curve is the equivalence point, because that allows you to determine the concentration of the unknown acid or base used. Because in this case, we know our acid concentration, we know our acid volume that was used. We should know how much base we used, and so we can determine the concentration of base using our equation MaVaIa equals MbVbIb, or just knowing moles of acid equal moles of base. 0.1 times 0.050 is my moles of acid used, which is equal to my moles of base. The second most important, or the other important part, is the halfway to equivalence point, because I can find my Kb or Ka of the acid. I can calculate the pH or find the pH using a pH meter. And if I know my pKa, I can find my Kb by using Kw equals Ka times Kb. Or 14 minus pKa is equal to pKb. So this one, I am starting with an acid because I'm starting with a pH less than 7. But again, I can't tell if that's a strong or weak acid until I look at the equivalence point. My equivalence point is 7, which means this must be a strong acid. And I still have halfway to equivalence because it's equivalence at 100, so halfway is 50, But the halfway to equivalence point for strong acid by strong base titration isn't really as important as it is for weak acid because we don't have pKa values. But at my equivalence point, my moles of acid still equal my moles of base, and so I can figure out the concentration of the strong acid used. My pH is 7 because all that remains is a neutral salt, because the conjugate of a strong acid is a neutral salt. So here we know we're starting with a base. We look at the equivalence point, and our equivalence point is 7, so I know that this is only a strong base. Would determine my pH at the beginning. Again, this is my halfway to equivalence. And any point after the equivalence, only the excess strong acid affects pH. Just as the previous problem, the conjugate of a strong base is a neutral salt. So I have a neutral salt at the equivalence point, which is why my pH is 7 at the equivalence point. And finally, this one, we're starting with an acid. We look at the equivalence point. It's above 7, so this must be a weak acid present. So since it's a weak acid, my pH equals pKa at the halfway to equivalence. Just like before, technically I have max buffering in this section here. My equivalence point is above 7 because only the conjugate base of my weak acid remains at the equivalence point. Everything else has been neutralized. So any point after the equivalence point, I have my weak conjugate base and my strong base. But my strong base is going to be what affects the pH. For polyprotic acids and amphoteric substances, some acids such as H2SO4 and H3PO4 can give up more than one hydrogen, but they only give up one hydrogen at a time. They're called polyprotic acids. Poly, more than one, protic, hydrogens. Once it loses one proton, it's going to become a weaker and weaker acid. So H2PO4 negative is a stronger acid than HPO4 negative 2. H2SO4 is a strong acid, while HSO4 negative is a weak acid. So when trying to calculate the pH of a polyprotic acid, you really only have to account for the first hydrogen. H2SO4 is the only exception because HSO4 negative is actually a rather strong weak acid. And then some substances can act as an acid or a base. They're called amphoteric. Water is an example of amphoteric. Sometimes it gains a proton to become H3O. Sometimes it loses a proton to become OH. You'll need to be able to interpret polyprotic graphs. You don't have to be able to do any calculations involving a polyprotic graph, but you do need to know how many hydrogens the acid had and some key points along the way. So the first thing, this curve has two bumps. In other words, I have two equivalence points. Since I have two equivalence points, this must have two hydrogens, or is a diprotic acid. So if I had H2CO3, at the very beginning I only have H2CO3. Then it starts losing a hydrogen to turn into HCO3 negative, and so I have both of these present throughout all of this line into the equivalence point. At the equivalence point, I only have HCO3 negative present. This first halfway to equivalence point would be my pKa for H2CO3. Then HCO3 negative will start to lose another hydrogen to turn into CO3 negative 2. So then I have these two present throughout this whole section until I reach the second equivalence point. So this pK2 is for HCO3 negative. And then any point after this second equivalence point, I only have CO3 negative 2 and the strong base. So my pH would be determined only by the strong base present. So go ahead and pause the video, answer the questions on the bottom. Restart when you're done. So we have two equivalence points, so there should have been two hydrogens. The arrow is pointing to the equivalence point, or the first equivalence point. pH equals pKa, halfway to the equivalence point, or the first equivalence point. So we're just going to say that that is point A, and this one's point B. So this one is A, and pKa2 would be at point B. So again, my equivalence points are the vertical sections. So halfway volume-wise to reaching those are when pH equals pKa, because I'll have equal amounts of my acid and base, or acid and its conjugate, I should say. So you have two beakers, both have a pH of 3. One has HNO3 and the other contains oxalic acid, H2C2O4. Go ahead and compare their ionizations. Restart when you're done with A. So HNO3 is a strong acid, and like we've talked about at the beginning of this video, strong acids break apart 100%. While oxalic acid is a weak acid, so it's going to break up very little. It's going to break up less than 5% at most. So if both beakers contain the same volume of acid, what can be said about the concentrations of the two acids if they both have a pH of 3? Go ahead and pause the video and figure out what you would put for B. Restart when you're done. Well, if they both have a pH of 3, my concentration of H has to be the same, 1 times 10 to the negative third. Well, my strong acid breaks apart 100% to give me that concentration of 1 times 10 to the negative third, while my weak acid would have to break up a whole lot more to produce that same amount of H. So I must have way more H2C2O4 to have the same concentration of H as I do for HNO3. So you can have the same pH in a weak acid and a strong acid. You just have to have a much larger concentration of that weak acid compared to the strong acid. So C, how much base is needed to reach the equivalence point in the titration? So this one was a little tricky because most people think, well, a strong acid is going to require much more base to neutralize it than an acid, when in reality it requires the same amount of base to neutralize a strong acid or a weak acid if they both have one hydrogen. But in this case, I have 2 hydrogens on my weak acid. Therefore, the weak acid, oxalic acid, would actually require twice the amount of base to neutralize it. Even though it's a weak acid, in the presence of a strong base, it's going to keep pulling off hydrogens, and as those hydrogens react with the hydroxide, it's going to keep driving the reaction to the right, breaking up more and more of the oxalic acid. Had this been any monatomic weak acid, it would have required equal amounts to reach the equivalence point. And remember that at the equivalence point, moles of acid equal moles of base. Nowhere in that does it say moles of a strong acid or moles of a weak acid. Go ahead and read through this page. Restart when you're done. So some key takeaways are what I've written over here on the left. The higher the electronegativity, the weaker the HX bond, making the acid stronger. So HCl would be stronger than HS because chlorine is more electronegative than sulfur. The more oxygens in an oxy acid is going to weaken that HO bond, making the acid stronger. So HClO3 is a stronger acid than HClO2 because HClO3 has more oxygens, which is going to pull the electron density away from the HO bond. So the key here is weaker H bond makes the acid stronger because the hydrogen will come off as a hydrogen ion in solution, and we want lots of hydrogen ions to have a strong acid or a stronger acid. On this first one though, the higher the electronegativity, remember that we've talked about it already twice now, that the larger or longer the bond length sometimes also affects the acid strength. So sometimes you may think that an acid should be strong like HF because it's very electronegative, but because fluorine is so small, it actually is able to hold on to that fluorine, making that bond actually really strong so the hydrogen doesn't come off. So go ahead and pause the video and answer these two. Restart when you're done with those. So we were looking for the strongest acid, and our strongest acid is going to be A because it has the most hydrogens on it. Remember that we said a few minutes ago that the acids for polyprotic, H3PO4 is the stronger acid, and acid strength goes down. So this one would have Ka1, Ka2, and Ka3. Every time it loses a hydrogen, it becomes weaker. And then for the second one, the only thing they differed by was the element in the middle. And the more electronegative the element, the stronger the acid, but we want the weakest acid. So our weakest acid would have the lowest electronegativity. Again, that's what we would predict, but if they had said that this was actually the strongest acid, we would say, oh, well, it must be because I is so large, it weakens the HI bond. Go ahead and pause the video and read through this slide, paying again close attention to the underlined sections. So here we have a carboxylic acid and amino group on an amino acid. They said that the pH of blood is 7.2. They want to know what is the expected ionization state of this amino acid for the free amino acids in blood. So NH3, we have 7.4 is our pH of blood, and that is lower than this pKa range. So NH3 should be in its acidic form. Well, we have two forms here. Acidic is going to have more hydrogens. So this is the acidic form. This is the basic form. We can't say 7.4 is a base because it's above 7. We're relating that to the pKa range. So since it's on the lower end of it, that's the acidic range. So we can eliminate A and C. Carboxylic acid, 7.4 is over here in the basic range. This is my acidic form of it. This is my basic form of it. So the answer is D. You're going to read this slide quickly and then restart. So a buffer is a solution with a very stable pH. We can add an acid or base to a buffered solution without greatly affecting the pH of the solution. The pH of the buffer will also remain unchanged if the solution is diluted with water or if water is lost through evaporation. But it's not going to be as good of a buffer if it's diluted, because we're going to have lower concentrations of our acid or base. But if water is lost through evaporation, then our concentrations become greater, and therefore it becomes a better buffer. In order to have a buffer, we need a weak acid and its conjugate, or a weak base and its conjugate. To calculate the pH, we can use Henderson-Hasselbalch equation, which is located here. So pH equals pKa plus log of the base over the acid concentration. And this is an important part here. When you choose an acid for buffered solution, it is best to pick an acid with a pKa that is closest to the desired pH. That way you can have almost equal amounts of the acid and base, which makes the buffer as flexible as possible, meaning that we can add H or OH equally amounts and the buffer not change in pH. So first off, is this a buffer? If it is a buffer, is the pH greater than, less than, or equal to the pKa, whatever that may be? And if not, why? So in this case, we have a weak acid and its conjugate. We have 5 weak acid and 5 conjugate base. Since we have equal amounts of the acid and its conjugate, so first off, yes, it is a buffer, because again, we have a weak acid and its conjugate. And then to answer the second part, because I have equal amounts of my weak acid and conjugate, pH will equal pKa. So my HNO2 equals my NO2 negative. So when pH equals pKa plus log of 1, and log of 1 is 0, then pH will have to equal pKa. So is this one a buffer? Go ahead and pause and solve it. Restart when you're done. Well, this is a weak acid, and this is also a weak acid. So if I was to put an acid such as HCl into this solution, the pH would drop dramatically because I don't have anything to combat that strong acid. So no, because it only contains 2 acids, and a buffer needs both members in a conjugate acid-base pair, not 2 acids or 2 bases. And finally, go ahead and pause and figure out, is this a buffer? And if so, what its pH would be. So this is a weak base, and this is a conjugate acid. They're separated by only a hydrogen. So yes, because a weak base and its conjugate are present. To figure out if the pH is greater than or less than or equal to pKa, we needed to add them up. We had 3 of the base and 7 of the acid. Well, if I have more of the acid than the base, then my pH should be less than pKa. Because I have more ammonium than, or more NH4 plus than NH3, when NH3 equals NH4, then pH equals pKa. So when I have more of the acid than the base, the pH will be less than pKa. You can pause the video and read this about the Henderson-Hasselbalch equation. Restart when you're done. So they tell you that you have a buffer, and that buffer is 50 milliliters of 0.1 NH3 and 50 milliliters of 0.1 NH4Cl. So when we add a little bit of HCl, what substance will be present in a greater concentration? NH3, NH4Cl, or HCl. Restart when you have that answer and a reason why. So if you said NH4Cl, you are correct. And then B wants to know the net ionic equation that is responsible for the pH staying relatively constant. Go ahead and pause the video and do that one, and then we'll go back to A and say why that was the answer. Well, we're doing the net ionic equation. So chloride is a spectator. So my hydrogen, or my strong acid, is going to react with the basic piece of my buffer to produce my conjugate acid. Had I had my spectator still in there, it would have looked like that. But again, since it said net ionic, I needed to remove the chlorides, giving me this. And it's already balanced. So back to A. When the H reacts with the NH3, my NH3 is going to go down in concentration. I'm not going to have any HCl left because it's going to react all the way since I had less of it. And I'm going to be producing NH4Cl. So in the buffer, whichever one is reacting with the acid or base is going to go down, and the other piece of the buffer is going to go up in concentration. And it doesn't say it in the problem, but after it's done reacting, I'm going to have more acid than I do base. So if I have more acid than base, what we just saw on the previous slide, or on the previous problem, my pH would be less than pKa. Go ahead and pause the video and try this one about which acid we would use to create a buffer closest to 4.8. Restart when you're done. Well, of these acids, this one has a pKa closest to 4.8. So this one's around 4.8, so I would want to use that acid and its conjugate, giving me B. Potassium is a spectator, so that part didn't really matter. I just needed that acid and its conjugate. This first one, I have a -4 there, so my pKa would be less than that, so around 3 something, about 3.4. This one is -8, so that's going to be around 7.5. This one's -10, so it's going to be around 9.8. This one was -5, so that's why I knew it was around 4 point something. And finally, buffering capacity. Go ahead and read through those two pieces of buffering capacity. Restart when you're done. And then try this last problem to see if you understand buffering capacity. So for this one, you should have gotten C because I had 6 of the acid and 6 of the base. It has the greatest capacity no matter what is added to it. I can add an acid or a base. I've got equal amounts of both to neutralize it. While D had a little bit of the acid and it had a lot of the base. So it's good capacity for the base in case I add an acid, but if I add a base to this solution, I'm going to exceed that buffer very quickly. B had 4 and 4, so it was a decent buffer since I had equal amounts, but not as good as C. And A, I had a lot of acid, but very little base. So again, I want roughly equal amounts, and the larger the concentration, the better the buffering capacity.